So let's have a look at a simple cell in action. Let's take this one. We've got a zinc electrode and a lead electrode over here. And we're going to have a look at the fact that a chemical reaction happens which gives out energy in the form of electricity. First things first, what we need to do is have a look. Which is the more reactive out of zinc and lead? Well, zinc is more reactive than lead. Therefore, zinc will become, the zinc electrode will become the negative pole. In other words, it will begin to give out electrons flowing around here. We'll be able to measure them through the voltmeter. Now, if we wanted to, we could put something like a simple motor or a bulb or something there that would use that flow of electrons and would transfer it into something useful. The electrons flow through here, they come down here, and they end up here at the positive pole, at the lead electrode. And then they flow through the lead electrode and into the electrolyte. So why does the zinc electrode suddenly decide to give up its electrons? Well, it's a chemical reaction, and it's about which one wants to be an ion more. Well, the most reactive wants to be an ion more. So when we put it in these situations and we have a potential difference between these two poles, then the most reactive will begin a chemical reaction. That chemical reaction will allow these electrons to be given up. So if the zinc, which exists as zinc metal, starts to give up its electrons, it gives out 2 electrons here, and it forms zinc 2+ ions. The zinc 2+ ions will go into solution. So over time, this zinc electrode is just going to dissolve away because the 2 electrons will start flowing around the circuit, and the zinc ions will dissolve in the solution into the acid. So you'd have to keep replacing this zinc electrode. So once the electrons have flown around here, we've used the or measured the flow of electrons here as electricity. What happens when they get here then? Well, if this is an acidic solution, we know we've got OH- and H+ ions in there, and we know that we've got some kind of H+ with a compound ion. Let's say it's sulfuric acid. We've got H+ with SO4 2-. So we know that the compound ions they're really happy, they're stable, they're never going to win in this case. So that only leaves H+. H+ are now attracted to all these extra electron buildups here. The H+ comes in, it receives 2 electrons and bubbles off in the form of H2 gas, which we could test with a squeaky pop if we wanted to. And basically then you've initiated this chemical reaction and you've harvested electricity from it. It may look like an electrolysis cell, but it certainly is not. Let's have a look at another one. Let's say we've got magnesium and copper this time. Exactly the same setup, just 2 different metals. Well, magnesium and out of magnesium and copper, magnesium is the most reactive. So magnesium is going to form the negative pole, and it's going to give up its electrons. So the magnesium is going to form magnesium 2+ ions, and it's going to give out 2 electrons, which are free then to flow through the circuit and be used in any way that we want to here. Those flow of electrons is going to continue down here. So the copper is going to become the positive ion. It's going to have a positive pole. It's going to have a buildup of electrons. Well, if we have a look down here, then we've got the dilute sodium chloride solution here. Instead of an acid, we've got our dilute sodium chloride solution. So our dilute sodium chloride solution here, we're just going to use our simple rules here to see what's going to win the day and out of the positive ions we've got there. So in this solution, it's OH- H+, but it's also got Na+, and it's got Cl-. Well, because it says the word dilute here, then we know that the chloride isn't going to win because the halogen never wins when it's dilute. And anyway, we don't have to worry about the chloride solutions because they're negative. So what have we got? We've got H plus and we've got Na plus. Well, the sodium is more reactive than the hydrogen, so the hydrogen is going to come here and form hydrogen gas because the sodium wants to stay as an ion. So you've got 2H plus 2E minus makes hydrogen gas again, which is very similar to what we had here, exactly the same half equation. So the hydrogen is going to bubble off here. So that's two simple cells in action. Now, very often the exam board will ask you, how could we use a simple cell like this to check the reactivity of the metal? So for example, how could we check now whether zinc was more reactive or less reactive than magnesium? And there's two ways that you can do this. Number one is to check the voltage. Let's go back to here. Say I now replaced the magnesium metal strip. I kept everything else the same, but I replaced the magnesium with zinc. Because magnesium is higher in the reactivity series than zinc, what we would find is that when we had magnesium, the voltage would be higher because the difference in reactivity between our two bits of metal is greater. In other words, they're farther apart on the reactivity series. So one way to tell would be to replace magnesium with zinc, and if the number on the voltmeter went down, we would know that zinc was less reactive than magnesium. A second way that we can do it here is to check the direction of the current. So say in this case, we wanted to, we replaced magnesium with something that was less reactive than copper. Say we replaced it with silver. Well, silver would be less reactive than copper on our reactivity series. So we would then be able to, the flow of electrons would come this way. So we would find that the copper dissolved into solution, whereas the silver didn't. And we would then know the one that did the dissolving, the one that forms ions and electrons, is the one that dissolves in solution. So we would be able to tell. And both of those answers are great for the question, how can you use a cell to find the reactivity of metals? So find the one that you're comfortable with, find the experiment that works in your brain, and stick with that one. You only need to remember one of those two things. So let's have a look at a hydrogen fuel cell. Remember, we don't need to know in great detail how this works, but you do need to know the basics. So let's have a little look here. Let's say, here's where the fuel comes in. We just run this fuel here. In the middle, we have this membrane. And on the other side of that membrane, we have air being pumped in. Now, that's where we get our oxygen from. We also get a little bit of water from the air because there's always water vapor in the air. But what we really want is the oxygen. So we want hydrogen fuel in here, and we want oxygen coming in here, and it's separated by this membrane. Now, this membrane is so tiny that only H plus ions can get through. The hydrogen as H2 can't possibly get through here. Because the holes are too tiny in the membrane. Now, in our electrolyte between the membrane, we have OH minus ions, which is kind of the driving force of this chemical reaction. Because when we put the hydrogen fuel in, it comes up into contact with the membrane and it reacts with the OH minus ions in the electrolyte. It forms water and 4 electrons. So that chemical reaction is enough to split this H2 into 2H plus ions, and they can flow around this circuit here. Now, we can put anything here. We could put this in a car. We could use this to drive a car motor. That's how a hydrogen car works. that here is everything that you need to be powered by your electricity, in this case, your car engine. So the H plus ions go through the membrane, and the electrons flow around where they can be harvested. Now, on the other side, you've got your flow of electrons. So this would be your positive pole here. Your positive pole down here reacts then with water vapor. Remember that we've made water over here in the electrolyte, so there's water here, and there's water coming in from the air as well. So there's plenty of water to react. We combine it with the 4 electrons that are coming in, and we simply just make overall, we make some water, which comes out of the bottom here. So the OH minuses here are being replenished, but the water, which is the overall reaction up here, with 2 hydrogens coming in from here, from the fuel source, reacting with the oxygen that goes here, and it's making water which comes out here. So that's all you really need to know, is that hydrogen comes in, it reacts with the OH minus ions in the electrolyte. The oxygen, which is the other reactant, comes in this side. That reacts with the electrons and the water, and that ends up coming out as just unused water here, which makes a hydrogen fuel cell very good for, there's no greenhouse gases or anything like that. The major drawback is that hydrogen is a flammable fuel source, and how do we keep that safe? So that's the reason why we're not all driving around in hydrogen-powered cars that aren't polluting the environment. If I were you, I would memorize this, I would memorize this, and I would memorize this, because that's all you're ever going to need to know. That's all that's ever going to come up in the exam. Here's a few useful links. This PowerPoint presentation is on the Google Classroom. This is a YouTube video looking at the basics of fuel cells and how they work. This is a Tyler DeWitt video that explains in great detail, it uses an analogy about a summer camp and kids at a summer camp trying to get to each other and make out. It's quite funny, but it's way more detailed than you need to know. And these are 2 websites, Doc Brown and BBC Bite Size, that have exactly what you need to know, but in a written source for you people who like to read. That's it. That's all you need to know. Hopefully by now you should be able to describe a simple cell. You should be able to describe what drives the current. You should be able to predict the negative poles. Just look for the most reactive metal. You should be able to give half equations, and you should be able to just describe what happens in a hydrogen fuel cell. That's it for now. See you later, guys. Bye.